Hi, everyone. A few announcements first, and then we're going to finish up some stuff on continuing where we were with Bayesian statistics and especially moving into some text data analysis. Okay, so hopefully you've been working on getting your project teams in place. That's due tonight to fill in the Google form with your team's information. Homework 4 is due Thursday, as you know. And a new announcement, so this Thursday, Hans-Peter is going to be doing interactive visualization with us, and the lecture itself will be interactive. And so there's two easy things that you should do before the next lecture, for those of you who are able to attend in person at least. You want to download Tableau Public, it's public.tableau.com, and install that. That should be pretty quick and easy. And then there's a data file that we'll be working with in class on Thursday, so it's easier if you already have the data downloaded. bit.ly/CS109 data, and we'll post this. And did you put this on Piazza, or he's going to put, this will be on Piazza too, this information. Okay, that's for this Thursday's lecture on interactive visualization. Okay, well, I found this analogy that I really liked about MCMC. So, we just, in this course, we don't have much time to discuss. MCMC is Markov chain Monte Carlo. I only briefly described the idea, and I'm going to go into slightly more detail today, but it's a huge topic and not one that we have a huge amount of time for. But this is an analogy I saw on someone's blog between MCMC and mountain climbing or mountain exploration. So the idea of MCMC is that you're trying to explore this complicated distribution or this big complicated space. So I talked a little bit about the prison code example where you're exploring the space of all 26 factorial permutations for how to set up the code. And more commonly in Bayesian statistics, the space that you're exploring is the posterior distribution, right? So we know Bayes' rule says the posterior is proportional to likelihood times prior, but unfortunately to do the exact analytical calculations of the posterior distribution is often intractable. It often is tractable too, like we were doing some stuff with conjugate distributions. If you use a conjugate prior, it is fairly tractable. It may be easy to write down, like remember we had a beta and a binomial, and we just write down the posterior as beta. That's not a problem. But when we get to more complicated models, and we may not want to use a conjugate prior anymore, then the posterior distribution can be this very complicated high-dimensional space that you're trying to explore. And I think the biggest strength of Bayesian statistics is that you don't just get one number, you get a whole distribution, right? So we can answer, what's the probability that the parameter is between 1 and 3. We can give, find the median, find the mode, find the mean. Whatever summary you want, you read it off of the posterior. But in order to be able to get all that, strength from having these posterior distributions, you need to actually have the posterior distribution. Okay, so MCMC was the technique that really made it possible in the last 20 to 30 years to really do Bayesian statistics on interesting applied problems beyond the really simple ones. So the intuitive idea of MCMC is like you're exploring this space, and so think of these mountain ranges as posterior distributions that you're trying to explore. Okay, and for some posterior distributions, it's going to work really nicely, and it's easy to explore, like that one on the left that looks very, very pleasant and tranquil, and you can kind of imagine, gradually climbing up the hill and walking around there, and you get to see a lot of things, and you could explore the space. You don't just want to know where the peak is, usually. You want to understand the whole landscape, the whole distribution. Okay, and usually in MCMC, you make little moves, go a little bit to the left, a little bit to the right, a little bit, all around. It's like a random walk, okay? If you're not familiar with Markov chains, the intuitive idea is simple. It's just that you don't have to care about the whole past history of how you got to where you are on the mountain. You just care about where you are now, and then you can keep exploring in different directions. So you're exploring the space. The one on the right looks a lot more treacherous, right? Like, there's a bunch of peaks there, and there's a lot of cloudy areas. It seems like you'd easily fall into a pit somewhere. It looks cool, but it looks pretty dangerous. You know, fall down somewhere, and can you ever climb out of there? Or you might be on one peak, and there may be another peak that may actually be more interesting than the one you're on, but it's so far in the distance. Most Markov chain methods are kind of nearsighted. They're local rather than global. Like they don't see all the way over to the other peaks. They're just like looking around, you know. And then some MCMC methods try to be more ambitious and try to make huge jumps. So there's a big trade-off if you're designing an MCMC method. Do you want to make tiny little steps, or do you want to try to make big jumps? Okay, but if you make big jumps, you might be able to get further faster, but then a lot of times you'll just get stuck where you are and not actually be able to go anywhere. So there are a lot of trade-offs there. So I wanted to show an example that connects Bayesian methods to what we were doing earlier with hierarchical models and shrinkage and connect a bunch of the concepts we've been doing. So this is an example from a paper by Andrew Gelman, and I took some of the stuff I'm showing you now from this was a nice Python exposition. It's working through Gelman's example, but doing everything in Python. And you know, the notebook is there, so if you want to see the actual Python code for how to do this type of Bayesian analysis, it's all right there. So it's about radon, which is a gas that comes up from the ground, and it causes lung cancer. I think it's considered the #1 cause of lung cancer other than smoking. And different areas, you know, in the world, some areas have a lot of radon in the ground, and others have very little. And it's generally believed that houses with basements are more likely to have a serious radon gas problem than houses without basements. There are lots of things you could study, like, first of all, is what I just said true? That if your house has a basement, then you're more likely to have radon or more radon there. And also studying different, the spatial structure, right? For which different counties or cities or states in the US is this a bigger problem? Okay? So this is just one really nice example of the big picture question, which is when you're developing a statistical model, what information do you want to include and what information do you want to exclude, and how do you use that information? And that's really, I think, the biggest question in statistics is not should you be a Bayesian, should you be a frequentist, it's just what information do you want to incorporate and how do you want to incorporate it, and what assumptions are you willing to make? Those are the bigger questions. Okay, so a very simple model for this radon problem would be, so suppose we want to study the question of, is it true or not that if you have a basement in your house, then you're more likely to have radon, or you're likely to have a higher radon measurement? Okay, so the simplest approach there would just be linear regression. So this is the simplest possible linear regression model. Radon is just the measurement. So this is based on some actual data in Minnesota. They went to a bunch of counties in Minnesota, installed devices that measure radon, and then so for houses in different counties, measure the amount of radon. Okay? So here there's an intercept, there's a parameter, and this floor is just is 1 if there's no basement and 0 if there's a basement, plus an error term. Okay, so a very, very simple linear regression model. And that corresponds to just having one parameter. Well, the parameter here is alpha and beta, and that generates all the data, so that this is all the data on all the houses, all the radon measurements. So, you can do that, but that's an extremely crude model. This would be called complete pooling, because you're just taking all your data, you're making measurements at different parts of the country or different parts of Minnesota, put all your data together into one simple model. But that's too crude for a lot of questions you might be interested in, right? Because you're not only interested in the question of does it matter if you have a basement, you'd also like to know which counties have more radon than other counties. And more generally, you might have a lot of other variables or features that you're interested in incorporating into the model. And some of those may be specific to certain counties, so you want to have some regional information in there too. Okay, so you could go the other way and say, I care about each individual county because I think that there may be differences between counties. And so here we're setting up a separate regression model for every county. So C is the count. So think of C as the ith house in county C. And it has some intercept term that depends on the county. So it's alpha. Here it's just alpha because we just use one parameter. Here every county has its own intercept. Every county has its own slope and its own error term. So what this is just saying is, let's do linear regression separately on every single county, okay? So we're not sharing any information between counties. And this is a fundamental choice that you have to make in many, many statistics problems. Do you want to group things together and study them jointly, or just do separate regressions, all right? And so these are completely different approaches. Here, as a diagram, you have one separate parameter for each county, and it generates its data. Here, you have one parameter for everything. Okay, completely different modeling approaches. But these are two extremes, right? I already said some things that are bad about this first model, but the second model is also bad because, for one thing, there may be some counties where you only have measurements on like one house or two houses. So you may have a tiny sample size. And so, you know, you want to be able to share information. And, we might think that counties, especially if they're close together, or, we may want to it may be reasonable to think that there are some kind of common underlying radon levels for the state of Minnesota. And then, so that there's kind of an overall, here's what radon looks like in Minnesota. And then there are differences between counties. Okay, but if we're doing everything separately, we're losing all of the overall information we have about the state. Okay, so these are two extremes. Usually when you have two extremes, the truth is somewhere in the middle, right? So a compromise between these is partial pooling. Partial pooling looks like this. I took this model where we had separate parameters for each county. I still want to have separate parameters for each county because I do think there could be important differences between counties, but I give them a common structure. So we add one more level at the top of the hierarchy. So mu and sigma squared are some overall parameters. You use those parameters to generate parameters for each county, and then from each county you can generate data from that county. So that's a compromise between the two. And written out, as a more formal model, you could do something like this, where this is the same model we had where it's a separate regression for each. If it's just this line, it's a separate regression model for each county. But then we link them, right? We give them some common structure, like with the baseball players, right? Baseball players, they're independent of each other, but they still come from some underlying overall distribution of baseball players. And so this is why Bayesian and hierarchical go together nicely, because we give alpha sub c, so that's the intercept parameter for county C. We give that some normal prior, and then we give the slope parameter, beta c, some normal prior. And by doing this, we've given them a common structure, that there's some underlying distribution for these parameters, and they all come from that same distribution. Yes? How do you decide what distribution? Like, why is it normal? Yeah. Okay, great question. How did you decide? Well, that's the biggest controversy in Bayesian statistics, is where does the prior come from? I chose normal because it's convenient and it often works well. Ultimately, it's an empirical. The normal has a lot of nice theoretical properties that explain why, like the central limit theorem says if you add up a lot of independent things, it will look normal. So there is some theoretical basis for that. But mainly, it's just convenient, and then it gives us a model. All models are wrong, but then we can actually check, does the model make some useful predictions? Can we do something useful with the model? Also, a general thing that, we see over and over again is, you know, if you have a large amount of data and a prior that's not ridiculous, it's not going to matter much. Normal is going to be convenient. We could do something else, though, and we get similar answers, maybe just with more work. If we don't have much data, then the prior matters a lot, but then, you know, if you don't have much data, like, don't trust anything, right? If you don't have much data, whatever you're going to do is going to rely on some strong assumptions and be very uncertain. So, yeah. So what's going to happen here is that for counties that have a lot of data, it's not going to matter much that it was combining information from other counties. For counties that had very little data, it's going to borrow a lot from the other counties because you're more uncertain about it. So it does all that automatically. You don't have to make a judgment call like, you know, if you could say, well, some of these counties are tiny and they can't afford to have their own regression. Some are big and we can just do separate regressions. You don't have to judge which ones are big enough, which ones are not. It's all automated. Also, coming back to the prior, you could say, well, where do these are called the hyperparameters. It's the parameters of the parameters. Where does the mu alpha come from? Where does the sigma alpha come from? All these things. And then there's two choices you can make. Either, well, there's three choices, really. You could just make up some values for those, and it seems highly subjective to do that, but unless you choose, you know, ridiculously extreme values that, you know, that are completely implausible, you know, try to think about what values would actually physically seem plausible and then choose something that reflects your uncertainty. That will be fine to choose constants. Or in some problems, you actually go another level of the hierarchy. You could say mu alpha also has a distribution, and then, you know, but then that has its own parameters. And you know, I think it's a big question, how far do you take that? The other approach here would be empirical Bayes, which we talked a little bit about last time. That you could use the full data set to estimate these hyperparameters. Which has been a little bit controversial in statistics. There was a famous Bayesian who once said there's no one less Bayesian than an empirical Bayesian. But a lot of those controversies have died down because empirical Bayes, you know, generally gives you reasonable answers, and you can check, you know, use it to make predictions. It gives you reasonable methods, and it feels less subjective than just making up numbers. So the numbers are actually estimated from the data. Okay, so if you do that, again, this is the link to where I took these particular plots from, because I like the way he laid it out here, and you can read this later for details. But once you have this model, then, you know, you can use MCMC methods to generate the posterior distributions. These plots on the right are called the trace plots. This just means as you're running your Markov chain, then, you know, how are the values varying? The main interest, though, you know, these plots are mainly used just to diagnose, did the Markov chain actually work properly? But in terms of our scientific conclusions, what we're mainly interested in are these plots, which are the posteriors. So for each of the parameters in the model, you get a curve, which is great, right? You don't just get one number. Okay, like if you're running just least squares or something and you just get like one estimate and maybe a standard error. You get this whole distribution for each of these. And for example, you know, which one is this? Mu sub beta, so that's the mean. Notice these are all concentrated around negative values, and this beta, this mu beta is the mean for the, let's go back to the model. Mu beta is the mean for these beta parameters. And these betas are the coefficients in front of this floor indicator, which was defined to be 1 if there's no basement. Okay, so the fact that this is negative is saying that if you do not have a basement, then you're going to tend to have less radon, right? And it's telling you quantitatively how much are you going to expect that the radon amount would go down. So it's the distribution of those. Okay, so just a summary of advantages of Bayesian hierarchical modeling. It avoids the two extremes. Complete pooling is bad, no pooling is bad, generally, right? Generally, you want something that's a compromise. The Bayesian, machinery gives you regularization and shrinkage for free that, tends to improve the estimators. We've seen a bunch of examples like that, where if you're just doing maximum likelihood or just doing ordinary least squares and not combining information like this, you can get some bad answers. And, I also want to just point out kind of the nice interpretability of the model. Like, we're in this big data era, and it makes sense that if you're working with big data, you want a big model. Big model meaning you have a lot of parameters. But if you have, 1,000 parameters, how do you even keep track of all of them? Like, how do you even remember what your parameters are when you have thousands of parameters? They're completely unorganized in general. But if you're using a hierarchical model, you are organizing your parameters into a hierarchy like a tree, and it's easier to understand a tree than just like a list of 1,000 parameters. Another very important feature of hierarchical models is that if you have different variables at different levels, you can incorporate all that in a natural way. Like if you have specific information about some of the houses you studied, and those houses are in cities, and you might know things about the cities, right? The cities are in counties, so it's kind of this nested structure, right? Houses in cities, in counties, in states, in countries, things like that. And you can incorporate that kind of structure very, very naturally into the hierarchical model, and whatever measurements you're interested in incorporating, you just put it in at the appropriate level of the hierarchy. And then you can generate predictions in a very natural way that, let's say there's some new house that you don't have no data on that house. It will generate a prediction for you from that model. But you not only can you get information or predictions on new houses, you can also get predictions at other levels of the hierarchy. Let's say new county. By new county, I don't mean that someone created some new county. I mean that in your original data set, there may be some counties that you just have no data on and you never studied them, okay? But then you still want to make predictions of what do you expect you would see in those counties that you haven't visited. So you can make predictions at, whatever level you're interested in. Okay, so, hierarchical modeling is a very powerful framework, assuming you can actually do the computation to get the answer. Okay, so I wanted to talk a little bit more about MCMC without going into much detail, because we have a lot of other things to talk about too. But I just wanted to briefly describe the two most famous, most widely used forms of MCMC. One is called the Gibbs Sampler, the other is called the Metropolis algorithm. So I'll start with the Gibbs Sampler, which is a little bit simpler. The Gibbs Sampler, so you have this list of, so typically with the way MCMC is used with Bayesian statistics is that you're trying to explore the posterior distribution, right? So you're wandering around in this space. The space you're wandering is just consisting of possible values for the parameters, right? So for simplicity, suppose we just have two parameters, theta 1 and theta 2, okay? And we want to explore so the posterior distribution would look like one of those mountain ranges, right? You have a theta 1 axis and a theta 2 axis, and then there's some height that, reflecting how likely is that theta 1 comma theta 2 value. So it's like a mountain range type of thing. And you want to explore that. And so you can draw like, contour plots as you would see with like a map if you're hiking to explore that distribution. And what the Gibbs Sampler says to do is that we only change, so we start at any theta 1 comma theta 2, just start anywhere to initialize it. And then the question is, how do you make moves, right? How do you explore that space? Gibbs Sampler says only change one coordinate at a time. So either change theta 1 and hold theta 2 fixed, or the other way around. Okay, so from whatever state we're currently at, we draw theta 1 from the conditional distribution of theta 1 given theta 2. That just means that we hold theta 2 as fixed, we condition on it, and then we figure out what's the distribution we want to draw from to get theta 1. So we generate a new theta 1 randomly, but given, so we're conditioning on the theta 2. And then you flip it the other way around. Hold theta 1 constant, condition on that. And the way we do conditioning is it's just the definition of conditional probability or Bayes' rule. So we condition on theta 1, update theta 2, and then we keep iterating that. So update theta 1, hold theta 2 fixed, update theta 2, hold theta 1 fixed, and you keep going. If it's more than two-dimensional, you do the same thing, except you cycle through the whole vector. So if it's a 100-dimensional vector, you update theta 1 and you hold theta 2 through theta 100 fixed, and then you update theta 2 and hold the other ones fixed, and you keep cycling through like that. And so it requires some math to figure out what's the correct conditional distribution. But it turns out that in a lot of problems, especially with hierarchical models, it would be really, really hard or intractable to actually write out the full posterior distribution. But these conditional distributions that you need often turn out to be nice things that you can actually deal with more easily. So this picture just shows that the steps it takes, it's just a bunch of vertical lines and horizontal lines, because we're updating theta 2, then we update theta 1, update theta 2. So it can't move diagonally. It's only, move some distance horizontally or vertically, okay? And that's also the biggest limitation, is that it cannot move diagonally, right? So it's restrictive. It's not very flexible. And I found a nice animation for this. I'll see if this works. This is an animation of the Gibbs Sampler moving around, and you can see it's just, this lower left is actually showing, it's exploring the space, and this is kind of, plotting out, here's the values. This is for one of these regression models, similar to the one I showed you, where you have a slope parameter and an intercept parameter, and just kind of recording. So it's just, it's a random walk. It's exploring the space in a certain way, okay? There are many different random walks you could set up. Some of them are going to be more efficient than others. There's theory that says if you set it up in a correct way, if you run it long enough, it's going to converge to the right thing. But in practice, it's sometimes really hard to know, has the chain converged? Have you run it long enough? If you don't run it long enough, you may have a bad approximation of the posterior. So that leads to some hard issues. Okay, and here's the other most famous, most widely used MCMC method. It's called the Metropolis or Metropolis-Hastings algorithm. And it almost seems, I thought it was too good to be true the first time I heard it, in the sense that it's so simple. The idea is that you start with any Markov chain that you could come up with. So again, if you're not familiar with Markov chains, just think of some way to explore the space, some random walk through the space. That has nothing to do, that's called your proposal distribution. That proposal distribution, or the proposal chain, that initial chain has nothing to do with the stationary distribution that you're interested in necessarily. Stationary distribution is what the chain will converge to, which in this case, for the Bayesian context, is the posterior distribution. So what it says is start out with whatever chain you want, just that happens to be convenient to you. And then it's just one little modification which says, I pretend that I'm going to walk one step, make one move according to the chain I have access to, but before I actually make the move, I flip a coin. And if the coin lands heads, I make the move that the chain said to do. If the coin lands tails, I stay put. And the technical thing here is this probability. This is just the probability of heads for that coin flip, okay? So the idea is I have this chain that I know how to do that may have nothing to do with what I'm interested in, and I just flip a coin at each stage to decide whether to accept or reject what that chain said to do. And then you run that, and it turns out that, because of this clever choice of the probability of heads for the coin, it turns out that this Markov chain will converge to the distribution that you're interested in. So this is an extremely general way to create your own Markov chain whose stationary distribution, which is the long run, steady state of that chain, is what you're interested in. So that's called the Metropolis algorithm. It won an award. This was an article I found that's the top 10 most important algorithms of the 20th century. That's, of course, a highly subjective list. This was from SciAm, which is the Applied Math Institute. So it says Monte Carlo method goes back to 1946. And a bunch of people worked. It wasn't just Metropolis. Metropolis and a lot of people worked on this at Los Alamos. They cooked up the Metropolis algorithm. So that it's kind of the quintessential Monte Carlo method. You can read that article if you want to know what they thought the other 9 out of the top 10 algorithms of the 20th century were. But basically, this made it possible for Bayesian statistics to actually be useful in a wide variety of scientific problems, not something that's mainly of philosophical interest. Okay, and then here's an animation like the one for Gibbs, but for Metropolis, just to see how that's kind of different. Notice at the beginning it's doing nothing. It doesn't look very good. And okay, now it just started jumping around, and it's much jumpier than Gibbs. So at the beginning it didn't seem to be doing much. The reason is because this involves flipping coins, right? And if the coin lands tails, you just stay put, okay? The Gibbs Sampler never has those reject steps. Gibbs Sampler always keeps moving. The Metropolis, sometimes the coin lands tails, it doesn't go anywhere. And then sometimes it makes a bigger jump, rather than the Gibbs is more rigid, that it can only go horizontal or vertical. So it's a very different way of exploring the space, and so that's a huge area. But those are the two kind of most famous algorithms. Okay, and just a couple links, if especially for final projects, if you don't have to use MCMC, but if it turns out that it might be useful on your projects. STAN, I don't think there's an acronym. I think that they just named it STAN. That's a really recent, really powerful way to automate a lot of the MCMC stuff. And STAN is available in R and Python and various environments. It automates a lot of the MCMC process, so you don't have to go by hand and code all of the steps. Well, actually, you can code up a Metropolis or Gibbs pretty easily from scratch. But the problem with the Metropolis algorithm is how do you choose the proposal, right? That your initial chain that you're using. And this kind of gives you some good default methods to do that. And there's PyMC, which implements a lot of MCMC stuff in Python as well. So those would be my two suggestions, if you want to use MCMC, which you don't actually have to do, depending on your project. All right, so for the rest of today, I wanted to talk about text data as a increasingly important area of application. How do you understand bodies of text? How do you statistically analyze text? And so to start with an example, this example is important for the field in general. This was an early example, and I also like it because Mosteller, so this is an example due to Fred Mosteller and David Wallace. Mosteller was actually the founder of the statistics department here, so it's a good example to talk about at Harvard. But independent of that, it was one of the first examples of statistics applied to history, or we could think of it as data science. They didn't call it data science then, but it's really data science applied to history. It was also one of the early examples of actually applying Bayesian thinking to a real problem with real data. Some Bayesian stuff has been around for 250 years, but the early days it was more philosophical, and here actually answering real-world questions with it. So the question that historians had been debating for a long time was authorship of some of the Federalist Papers. And if you're not an American, or if you've forgotten your U.S. history, these are very important documents when the U.S. Constitution, they were trying to get ratification of the U.S. Constitution. And I think 1787, Hamilton and Madison were the two main authors of these. They wrote this series of essays that were trying to convince people to support ratifying the U.S. Constitution. Okay, and Hamilton and Madison wrote most of them. And there are 80-something of these documents, and for about 70-something of them, it's known almost for sure who wrote it, okay? But there were 10 or 15 of these Federalist papers where there were some, bitter controversies and sharply disputed about who wrote those, okay? So they wanted to answer the question of who were the authors of the ones that have unknown authorship, using statistics rather than, other previous historical approaches. And they actually wrote a book about this, and they also have the book is based on the paper, and there's a link to the paper here if you want to read more details. It's a very, it's an old paper, but it's a classic. It's very instructive just to see how did they think about the data, how did they think about the model, how do they check whether their conclusions make sense, right? Because there's too many papers that just, they just want to run they don't really necessarily even care about the data, right? They just want to test out their method. They want to try out their method, and they generate some answers, and they don't really check and think about the data and think about the model. So this is a really very thoughtful classic paper. So the link is there if you want to follow up. Okay, so the first thing you might think of trying to do is just compare, if you just want to do a linguistic analysis of it, is count words, right? Because maybe, so we wanted to determine for the 10 or so unknown essays, was it written by Hamilton or Madison? So you might try to say, okay, let's compare their writing styles. Maybe there's certain words that Hamilton loved and Madison never used, or vice versa. So we have training data, right? Training data is, the essays that we know actually who wrote it, okay? And we can compare their styles. So we can actually count, how many times did Hamilton use certain words or phrases versus how many times did Madison use certain words or phrases. These days, that's easy, right? And that, that's some of the skills that we were teaching earlier. And you can write a very short program that's going to count the number of occurrences of each word. There's always going to be some data cleaning involved with text analysis. To get download some text data, and then you break it up into tokens and study those. And you want to think about questions like, do you want to treat the plural of a word as the same? You want to look at just the root of the word and not distinguish between the plural and singular or different conjugated forms of the verb or things like that. So, there's always some cleaning to do. But back then, they didn't have computers to help with this. And I actually heard that this was around the time that shortly after the statistics department here was founded in 1957, and they were working on this in the early days of the statistics department. And I heard they enlisted everyone in the statistics department to literally just count words, right? Give you all the documents, and you count, right? You count this document. I don't know whether they split it up you do document 1, you do document 2, or you look for all the froms and you look for all the becauses, but it was all manual, okay? And so one thing I find amazing about this is just that they could actually do this. And they spent years, they spent 10 years working on this. And they joked about the fact that they spent a lot more time working on this than Madison and Hamilton spent actually writing the Federalist Papers. So they spent 10 years on this analysis that, I think it's something that's really cool that we're in this era where now we can just write 1 or 2 lines of code. We have fast computers, and you could generate a table of, occurrences of words, very, very quickly and easily. That's encouraging. I also find that a little bit depressing because, we have so much more powerful tools than they had, then why aren't we, doing things that are, a million times better? I mean, we've definitely done a lot of things that they were not able to do then, but we should be, a million times better because they had to spend 10 years just, tabulating words. Okay, so we should be, I think, further ahead than we are. So anyway, here's an example of data that, extracted from the known Federalist Papers. So it turns out that Madison did not like using the word upon. That's something they noticed. So, you know, obviously that wasn't the first thing they thought to look at. They tried many different words, and then they look and they found Hamilton used on and upon interchangeably, okay? Like on this day or upon this day. Hamilton, you know, flipped back and forth between those, but Madison always said on, not upon. So, well, almost always. So this is just a table of the distribution of the rate in different documents. Exactly zero, so the rate meaning number of times per 1,000 words does upon appear, okay? And so you notice that, you know, in 41 of these 50 documents that this is based on, Madison used upon 0 times. But in none of them did Hamilton never use that. So Hamilton is usually using upon a lot, Madison rarely. Okay, well, we've answered our disputed historical question, almost, because if you look at the 12 disputed papers, in 11 of the 12, upon never appears, and that seems a lot more like Madison than Hamilton. Okay, so this did not really require any fancy statistics. It's just like, you know, a lot of times you can gain insights without doing fancy statistical models. Just look at the data, explore the data. This is really exploratory. This is not inference yet. Explore the data and see, and it looks more like Madison. And in the end, that is what they did a lot of statistics, but in the end, that is what they concluded, that it was very likely to be Madison for most of those. There's also other possibilities. I mean, could they have collaborated and written it together, and it's not an either-or situation? But you can't be sure, right? Because, you know, it's not like Madison never used upon, right? You see some where it did occur, okay? And so, you know, it's hard to be, and you know, these are just samples, right? It could be that in this sample, you don't see Hamilton never using upon, but it could be that if you collected 1,000 essays by Hamilton, hypothetically, if you had 1,000 of them instead of 50, maybe you would find a bunch where upon doesn't come up just by chance, okay? So, you know, it's not entirely convincing. It definitely looks favorable towards Madison, but it's not really a probability statement. Like, I want to know things like, what's the probability that Madison wrote this essay, okay? And I want to know how confident I should be, right? And this is good reasons for thinking like a Bayesian. Like, as a frequentist, from a purely frequentist perspective, it's not even meaningful to say what's the probability that Madison wrote this document, because either he did or he didn't. We just don't know which. But a Bayesian can directly model our uncertainty, okay, our degrees of belief. So we can make statements about how likely is it that it was Madison, and we can quantify our uncertainty and try to be more quantitative and precise about it. And we can also develop method. Here it's kind of, you know, obvious, or it seems obvious from happening through exploration to find this word upon, but in other problems you're not going to be so lucky to find something that makes it so easy to see the difference between their writing styles. Okay? So they introduced a Poisson model. Not surprising that they wanted to use a Poisson as their first choice of model. So y here is the number, so consider some document. You're trying to determine whether this document was written by Hamilton or Madison, and let y be the number of occurrences of a particular word, for example, upon. Okay, so that's data that we observe. But that's just, you know, we just have a writing sample, right? We don't have an infinite amount of data. We just have some sample, and if they continued to write other stuff, you know, then we'd see that those numbers would change. So the actual data, you know, you would observe has some randomness and noise to it. And then, so that's why we introduce, you know, a parameter, lambda. So lambda is just saying, you know, hypothetically, or in theory, if that person wrote more and more text, at what rate would the word you're interested in appear? So if it's upon, you know, lambda would be the number of occurrences of upon per word or per 1,000 words, in theory. Okay, so Poisson is natural here because it's saying, you know, your document has a lot of words. Any one word there is unlikely to be the word upon, right? But you have a lot of them. That's exactly the setup where a Poisson makes sense. So use a Poisson model is a very natural choice. They also considered other more sophisticated models, but this is kind of the main building block model in this case. And they took a Bayesian approach, so we need a prior, right? The model is not complete until we specified the prior, okay? And the conjugate prior for the Poisson is called the gamma. The gamma density looks like this. It's lambda to a power e to the minus b lambda. It has two parameters, a and b. So this is just called a gamma distribution. And you can actually just see, I'm not expecting that you need to know anything in particular about the gamma other than what's on this line here. But you can actually see where it comes from, why conjugacy is going to work. Notice that the Poisson has e to the minus lambda and lambda to a power. And look at the gamma. It has e to the minus something lambda and lambda to a power. And remember what Bayes' rule says. The posterior is proportional to likelihood times prior. So this is the likelihood. The likelihood function is this thing as a function of lambda. So remember, for the likelihood function, we treat the data as constant because we observed it. View this as a function of lambda. So that's the likelihood function as a function of lambda. That's the prior. You multiply likelihood times prior to get the posterior. And so it's just this times this is going to be the posterior. And notice that the posterior is still of the same form as the prior because you combine, you know, it's lambda to a power, e to a power. It still looks the same. That's why it's conjugate. So that's the nicest choice to deal with. And again, it's not going to, you know, you do have the controversies of like, well, why did you do gamma rather than something else? And also, how do you choose A and B? And you could choose A and B using an empirical Bayes approach, or you could just pick some values that you know, don't seem too extreme. And it's not going to matter much what your prior is, unless you have very little data, right? If you have a reasonable amount of text, it's not going to be a problem. Okay, and so using that, you know, you can get a lot of pictures like this. There's just one example. This is the word from, and you get a posterior distribution. And I just wanted to illustrate, you know, the type of thing you get. And the dotted line is the likelihood, and the solid line is the posterior. And notice they look quite similar because the prior is not too extreme. The data speaks up for itself. So it's driven by the data, not driven by the prior. And they did a lot of explorations in the paper of like, what happens if you change the prior to this or that, and, you know, showing that actually it doesn't affect the conclusions much. Okay, so they concluded that it was very likely that Madison was the author on at least most of those. All right, so let's go on to some other text type stuff. That one of the initial, you know, early concepts in text data analysis was the idea of an Engram. This comes up a lot in natural language processing, where it's a very simple idea. So suppose we take a sentence like data science is fun. I just made up a sentence, okay? Just to have the definition. The Engrams means we look at n tuples of words. So we take, you know, n words at a time. So for a unigram, it just means we're looking at one word at a time. Data science is fun. Bigrams means we're looking at two words at a time, consecutive, right? So I want to know which words tend to occur commonly in pairs, right? So data science is fun. So I just looked at all the pairs of that sentence. For a trigram, you would look at three at a time, 3 words at a time. So data science is fun, okay? And I guess you could do a 4gram here too, data science is fun. Now, I just made this up to be a really simple example. It's only a 4-word sentence. But imagine that you had, like, you know, a 20-page document, or you might actually have thousands of, these days you can, you know, easily download a collection of documents that's going to be, you know, thousands and thousands and thousands of pages, okay? So you could go through that and then look at the unigrams would tell you, you know, how often does each word appear, and then the bigrams would tell you how often does each pair of words appear, because some words very commonly are, you know, followed by a certain other word, right? Some pairs are common, some pairs are rare, okay? And so if you have thousands of pages, then it would make sense to start looking at, like, you know, trigrams and 5 grams and by the time you get to like 5 grams or 6 grams, you're actually going to have a lot of sentences, right? If there's a sentence that occurs a lot, then, you know, well, you'll start seeing sentences. All right, so this is just a way to break up a document into chunks and then look at how often do those chunks occur. So, for example, this was from a blog post I saw where the author took all the text of The Hobbit by Tolkien, broke it up into Engrams, and then generated. The cool thing you can do with this is once you've found the Engrams, then you can actually generate text, right? It's generative in the sense that you can then, once you've figured out like how often does each Engram appear, then you can generate, okay? So into trees and then bore to the mountain to go through, groaned the hobbit, well are you doing, where are you? Okay, so you get a lot of gibberish, right? But as you increase n, it's going to make more and more sense. And I like this too. He used Engrams to mix together the Hobbit and the Cat in the Hat. So what he's doing here is taking all the Engrams, you know, from the Hobbit, all the Engrams. I forgot what he chose N to be here, but I'm sure it's mentioned in this post. Okay, he picks some Engrams from the Hobbit, some from the Cat in the Hat, and then randomly choose, am I going to do something from the Cat in the Hat or from the Hobbit? Okay. Oh, you can read that for yourself. So you can do fun things like that, where you're you know, mixing together different texts, and you know, well, it's fun to do, but hopefully you could also get some insights about writing style from this. And here's one more Engram example. This one is from the book Data Science from Scratch, which is a nice O'Reilly book. So what he did here was he took a paper about discussing what data science is, and then he looked at the 2 grams, which is bigrams, and then generated something from there. So, okay, if you may know, so at first, like if you just look at this, it looks like English, and then if you actually carefully read it, it doesn't make any sense. If you may know which you wanted data, sort the data, feeds, web friends, someone on trending topics. The data in Hadoop is the data science required, blah, blah. Okay, so it's actually gibberish. But you sort of look at it and kind of see, like, you know, what types of words are appearing a lot, basically. All right, and then I wanted to show you what happens if you go from a bigram to a trigram. In hindsight, MapReduce seems like an epidemic. And if so, does that give us new insights? And so here it's actually almost sounding like not complete gibberish, even with trigrams, into how economies work. That's not a question we could even have asked a few years. There has been instrumented. Okay, so it's still gibberish, but not quite as gibberishy, because it's picking out, you know, these chunks that actually make sense. And if you go to higher and higher, then it's going to start stealing actual sentences. All right. So this is useful for exploration and getting a feel for data, but it's not really letting us do statistical inference. It's not really a model. It's just a kind of way to look at what commonly occurring phrases. So for the rest of today, I want to talk about actual modeling, and an approach that's quite recent but has been very influential and found a lot of applications is topic modeling. A specific model for that is called a latent Dirichlet allocation, and I'll explain what that model looks like. This picture and a lot of the ideas here are from David Bly, who's at Columbia in Statistics NCS at Columbia, who wrote the most influential paper that kind of got this latent Dirichlet allocation stuff going. All right, so the idea is this, that you have a collection of documents, okay? Like, for example, take a journal, a scientific journal, and all the papers that were published in that journal in the last 10 years or something like that. So you have a collection of documents, and you want, you know, an automated way to discover what the topics are, and then to describe each That's the goal. So the goal is to discover what the topics are, hopefully discovering some interesting things there. And then for a particular paper from that journal, so a particular document, you want to describe it like is that a data science paper? Is that a genetics paper? Or is it a mixture? Is it a paper that applies physics to genetics? You know, you want to kind of describe these things. Okay, so, you know, this is just kind of a schematic for, you know, you have like some histograms, and so here's an actual document, and then you kind of break it down by topics. So for the words that appear there, highlighted in yellow, they got grouped into this topic, and then the pink ones got grouped into this topic. So the idea is that each word in this document is coming from one of these topics, okay? And in some topics, certain words appear a lot. Like if it's a genetics paper, it's not surprising that you're going to see words like gene and DNA are going to appear a lot, right? You know, if it's a brain, if the topic is the brain, well, you expect to see a lot of stuff about neurons and things like that. Of course, there may be overlap. There may be words that are commonly used in multiple topics. So not only do you want to be able to say, this paper is, you know, 30% about genetics, 20% about evolution, 10% about the brain, you know, 40% about computing, things like that. So you want to kind of describe it as a mixture. So take any document, you want to be able to automatically describe it as a mixture of topics. But the biggest challenge from this is that it's unsupervised in the sense that you're not given the topics in advance, right? You have this collection of documents, and you're not telling it that these are the topics that I'm interested in. I'm not telling it that genetics, I'm not telling it that it's a journal that publishes a lot of genetics papers, and genetics should be one of the topics. You know, it's trying to automatically discover the topics and then say for each document, what mixture of topics does it have, okay? So it's pretty cool that that's even possible to do in a reasonable way if you have a large collection of documents. There are a lot of parameters in this model, so it's going to make a lot more sense if you have a large collection of documents, like, for example, this is also from David Bly's paper. He took 17,000 papers from the journal Science, and you don't choose in advance what the topic, you don't choose in advance or say in advance what the topics are going to be, but you do have to specify in advance how many topics you want it to find. So he downloaded 17,000 articles, and then he said, let's do 100 topics. And then the method automatically comes up with 100 topics. And the topics are described basically by the lists of words that appear very commonly in those topics. And then a human being actually named these topics. So like the method comes up with this list and this list and this list and this list, and then a human said, well, this looks like a genetics topic, and this looks like an evolution topic. This looks like it has to do with computers, that kind of thing. So, you know, sometimes you'll get topics that don't really seem like a topic to a human being, that it, you know, doesn't make much sense. But often you'll get lists where you actually do have a nice interpretation, and that does feel like something a human being would consider a topic. And so it generates, you know, lists like this, and of course, you know, you can rank these and also describe, you know, how the probability of each word within a topic. And then for this histogram over here is just showing, for this particular paper that he was looking at, how common, representing as a mixture. So like this one is, you know, on the horizontal axis is just the topics, and then saying, you know, well, there's, what, 50% chance of being this topic and a 15% chance of being this topic. So for each individual paper, you can draw a picture like this that's a plot like this describing it as a mixture of topics. So it's interesting for two reasons. One is that you can understand kind of the individual documents as mixtures, and the other is just discovering these topics in the first place. All right, so this is called latent Dirichlet allocation, and there's this is a very nice exposition of it that you can read later. I took this picture from there because I liked, well, it just looked nice to me. But let me explain this. This picture actually, in a nutshell, is the difference between probability and statistical inference. So it's actually a very, very fundamental picture for text analysis, but for statistics in general. The idea is you have a model, and we've been talking about models, right? We talked about hierarchical models and Poisson models with a gamma prior. You have some generative model over here, which is how you hypothetically could generate data, right? All models are wrong, but some models are useful. So this is some hypothetical way for how we could generate data, and from that you could generate fake data, okay? That's probability. That's probability modeling. And in statistical inference, we're going in the reverse direction. We have data. So in this case, our data would be a corpus. It's just a collection of documents, right? So you have these 17,000 documents that you downloaded. That's your data. You don't know, you do have a model in mind, but you don't know what the parameters of that model are, okay? And then you use statistics and machine learning methods to estimate the parameters. And once you've estimated the parameters, you can actually keep circling around, because once you actually have estimated parameters, then you could generate fake data using those parameters and see, does the fake data look like the real data? Because if the data that you generate looks nothing like the actual data you have, then probably your model's not very good. And then you can keep iterating, so you can keep going around and around like that. Okay. So let's start by describing the generative aspect. That is, I'll describe the latent Dirichlet allocation generative model. Here's how you would generate data, fake data, right? But you know, the name latent Dirichlet allocation suggests it has something to do with something called Dirichlet, which we haven't described, and I'm not assuming you've seen it before. So I'm not going to go into all the mathematical details about the Dirichlet distribution, but I just wanted to briefly describe it. We have talked about the beta distribution. So remember, for the binomial distribution, the nicest choice of prior is the beta. So it's the beta distribution, it's a distribution for a probability, right? The probability itself is random. And the Dirichlet is just the analog of the beta in more than one dimension. So we're putting probabilities on probabilities. And this picture here, that's called the simplex, and we're thinking of it as, we're looking at points in 3 dimensions where the components sum up to 1. So we have these extremes, 0, 0, 1, 0, 1, 0, 1, 0, 0. But you could take any point in 3 dimensions where the sum of the coordinates is 1. And because we're thinking of a probability vector, right? We want something where like, we want to consider a document where the document might be 30% about genetics, 20% about chemistry, and 50% about statistics, right? So we want some mixture. So I made up 3 numbers, 30%, 20%, and 50%, that add up to 1. So to describe for one of these documents, you know, what mixture it is, we need to specify probabilities that add up to 1, okay? And so we need a distribution for those, and the most famous distribution like that is the Dirichlet, and it's analogous. I'm not going to write down the mathematical formula for the density. You can look it up easily, but it looks like a beta, except you have more terms because it's not just one probability. So that's the Dirichlet distribution. All right, and here's the generative model. I'm not actually going to go through this looks really complicated. So part of the reason I'm putting this up is just to show you how much better it is to have an example and a picture for explaining this. So notice, I'm not going to go through all this right now. I just want to point out, there's a lot of parameters. I just took this description from Wikipedia, but you know, it's a correct description of the model. There's a lot of parameters, and then this is the generative process. So this is an algorithm for generating a random document. It's telling you how to generate the words. And notice there are a lot of DIRs here. That's the Dirichlet distribution. So it's based very heavily on the Dirichlet distribution. Multinomial is just the analog of the binomial in more than one dimension, and the idea, but in this case, is actually a simple form of the multinomial. All it really means is that, let's say you have the paper that's 30% genetics, 20% something else, 50% something else, okay? And what you're going to do is you're going to go word by word if you're trying to generate a fake paper, right, using that distribution. You go word by word, and for each word, you decide randomly, is that going to be going to come from the genetics topic, or is it going to come from the chemistry topic, or from the statistics topic? And once you've decided that, let's say it's genetics, then you choose a word from the genetics topic with probabilities given by whatever the probability distribution is for genetics topic, right? So in a genetics topic, there's some probability that the next word is going to be DNA, and there's some probability that the next word is going to be phylogenetic, and so on. And you generate randomly from that. And it's actually, this looks complicated, but it's actually an incredibly simple model in the sense that from one word to another, it's actually independent. So it's much easier to understand through an example. And this is this URL I gave here gives a nice intuitive explanation of a lot of aspects of LDA, so you can read that for more detail. But I like the way he wrote out this example. So this is how you would generate, let's say we only have two topics, food and cute animals, okay? And we want to generate a document using that. And first choose the number of words, say 5, okay? And then we choose, so D is the document, okay? So we're going to generate a 5-word fake document, okay? So 5 words, and then we need to choose how much of this document is about food and how much of it is about cute animals, right? And we choose that randomly. In this case, because there's only 2 topics, you could actually use a beta distribution. You could generate a beta random variable, and let's say you got 0.7, then you say, okay, it's 70% about food and 30% about cute animals. Okay? So you randomly determine what the mixture is. More generally, it's a Dirichlet. That's just determining what mix of topics are there in this document, because we're generating one specific document. Okay? So just for example's sake, let's say we decide it's going to be 50% food, 50% cute animals. Okay, then we just go word by word. And for the first word, we say, okay, I'm just going to flip a coin to determine is that word about food or is that word about cute animals. Okay? And let's say it's supposed to be about food, and then we know we need to generate a word about food, and we look in our distribution for the food topic for what words are used for food and with what probabilities, and then we generate a word, say probability. Then you go to the next word, and just independently, okay, I'm going to flip a coin again to decide whether it's about food or cute animals, okay? And I'm going to generate, right? And you can just keep going like that, okay? So this is the generative model, right? And there's a nice picture. I think the picture is easier to understand than that formal statement from Wikipedia. It still takes some time to understand because it's easy to get mixed up about what's happening with the topic versus the document versus the word. You have to be clear about what parameters apply to what. But the idea is you have some way to generate the mixture distribution for the document. So I want to generate a random document, okay? So I first look at a mixture of topics, and I use Dirichlet's to decide, is it going to be 30% genetics, 20% physics, blah, 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 or is it 10% genetics and 40%, right? I generate that mixture first, okay? And then I know what kind of document I have. And then for each word, I generate what topic is that word going to be from, and then I generate the word, okay? And there's also word distributions per topic. That just means for each topic, I need to know within that topic how often do you use certain words, okay? Those are the ingredients. And so then you generate a word, and then you just keep doing that until you have a document of the length that you want to have. Okay, so that's the generative model. The inference part is going in reverse, right? So in inference, now we imagine that we have 17,000 or whatever documents, and we want to estimate the parameters and discover the topics, okay? So the technical details of that are harder, and I'm not going to go through all the math for that, partly because it would take too long and be too much math, and partly because if you want to do topic models, there are nice Python and R and libraries for doing this stuff, so you don't really need to understand all of the technical details. You can just try it out. I think it really helps to understand what the model is doing, though. It's also called a bag of words model, which just means that you're just at first sight, it seems like too naive to be really useful in the sense that we're not saving the structure of what word follows which one. It's just, the reason it's called bag of words is you take your document and just get all the words and dump them into a bag, and you don't retain the ordering of the word. And it seems like we're losing a ton of information there. And we are. But there's also a ton of interesting information there just from looking at how often do different words appear. And especially when you have a lot of documents, then you can kind of create these topics. Okay, so it's very important to understand the generative model. I think it's less important to understand all the technical details of the inference stage. But the idea is think like a Bayesian, because we have Bayes' rule, right? So this tells us, this generative model tells us, given the parameters, here's how we could generate the data, okay? And then for the data analysis, you go in the reverse direction. But Bayes' rule tells you exactly how to do that, right? The posterior is proportional to prior times likelihood. So you need to come up with there are a lot of parameters in this model, but you come up with some prior distributions on the parameters, you know, do likelihood times prior. The generative model tells us the likelihood. You multiply by the prior, that's the posterior, okay? In principle, that's it. In practice, the computations can be hard, and so there are a lot of ideas. It's actually based on the Gibbs Sampler, are some of the major ideas that people use for the actual, you know, to actually fit it. It's based on Gibbs samplers in many cases. But in principle, it's just, you know, do your Bayesian updating. And Gibbs Sampler helps you to actually do the calculation. And you don't have to write those Gibbs samplers from scratch. They're implemented for you in various useful libraries. Okay? So just wanted to do another quick example. This was from something I saw in the New York Times, and I highly recommend reading this whole article, so you'll have the link. But they actually use recommendation systems at the New York Times for the New York Times Online to recommend which article you should read, so that's a recommendation problem. So they're alluding to things like collaborative filtering and things like that. It kind of ties together with stuff we were doing earlier. And they even talk about LDA, which I was pretty impressed. I wasn't expecting in the New York Times to see something that seems pretty technical, latent Dirichlet allocation. They actually talk about it here. And it's kind of a cool example seeing how the recommendation, because they have a lot of users, obviously, of the New York Times, to see how their recommendation system for which article to read relates to the topic modeling and text analysis question, because the New York Times has a lot of articles, and you know, you don't want to manually for each one say that that's 20% about politics and 30% about art and things like that. It would be a lot nicer to automate that. And so there's just like a picture kind of showing how these things come together, where, you know, you have a topic here for art, home, and life, and another topic for politics, American, and government, just so that they could visualize it in 2 dimensions. And then plotting, you know, these blue dots here are, you know, specific articles like, you know, Frick Museum abandons contested renovation plan. You know, it's some point here. So the LDA will let us describe for each New York Times article what combination of topics does it involve. But then this red X here represents an actual user. So this is someone who, because the New York Times has data on what types of articles does that person read, and it's oh, this person, you know, reads politics articles, you know, 40-something% of the time, and art, home, and life articles like 60% of the time. So they're putting people on the same axes with the documents. And then one very simple way to recommend articles is I'll just recommend to this person, I'm going to recommend articles that are nearby in that space. it's a very simple thing to do. You can probably think of better things to do too, because it's like, if I like to read papers about art half the time and politics half the time, it doesn't actually mean that I want to read papers that are half art and half politics, right? I might want to read 100%, like maybe I don't want them mixed, okay? Because that's specifically looking at that kind of a mixture, and So, but the point is that we can describe, using some similar sets of labelings, both the users, what their preferences are, and what the actual documents are describing. And then one more example from this article, which I thought was kind of funny. So again, they're looking at politics, American and government topic, and then travel, safety, and automobile. And so there was this article called Dogging Mitt Romney, and the problem that they noticed with their method, so they were just doing LDA, latent Dirichlet allocation. The problem is that this article was, it's about, there was a famous, anecdote or controversy that Mitt Romney strapped his dog to the roof of his car and drove to Canada with the dog on the roof. So the article is all about talking about, dogs and animal stuff, and it looks like, so that document got classified here, that it's mostly about travel, safety, automobile, and if we had another dimension here to show pets, right? So it's about pets and travel, right? Because you're traveling with your dog. But actually, the whole point of that article is it's about Mitt Romney, right? And the LDA does not pick up on that. So they had a kind of cool way to adjust for that, which is they looked at, here are the readers who actually read that article. And look at where these people are. These are the people who like to read about politics, okay? So, because of that, you can make up you can make up an automated way that would try to move this from here to here would be a better, just based on the fact that there's all these people here that, if people who like politics are the people who are reading that, right? Not people who are interested in travel, okay? So I thought this was cool that the kind of combination of the LDA stuff and then recommendation stuff, basically based on looking at who actually read that article. All right, well, this is going to be a perfect lead-in to the next lecture. How do you visualize LDA? Usually when you see visualizations of LDA, it's not really a visualization, just people will give these lists of words, and I've already done some of that, where just like, look at the words, okay? But it would be a lot more informative if we try to rank the words and show, people just give like list of topics, list of words. And this is a really cool, there's links here. This is actually I'm not going to show you the interactivity right now, but you can go to the links and try it out. So this example is from the corpus. The documents consist of movie reviews. Okay, so they used LDA to discover topics in movie reviews, and so this is one of the topics that came up, automatically, and you can kind of call this the comedy topic, because it says comedy, but it says funny, jokes, comedy, Truman, Carey, humor, gags, joke, hilarious, well, all this stuff. This was all automated, through LDA, but it looks like this topic is about that, the movie is a comedy, right? And so you could describe, okay, is this movie or is this review kind of referring to comedies or dramas or things like that? And this is just, I think, a really nice way to actually show, here's the different, most relevant words, and there's some parameters you can adjust that kind of describe relevance, because you can find words, one thing that has to be accounted for is you can find a word that is maybe the #1 most commonly used word in that topic, but that might just be a common word anyway. Well, I didn't mention, but one thing you need to do in the data cleaning stage for this LDA is you get rid of what's called stop words, which are words that are extremely common in any topic, like the, of, but, and. You filter all of those out first. Anyway, So you can look at, kind of the overall frequency of that word as well as the frequency within the topic. And this is doing a multidimensional scaling of the topic. So this is kind of describing or, showing how the different topics are distributed. So you have to tell it how many topics do you want. And then once you do that, it discovers the topics. And, here it's plotting them using MDS. And originally this was an R package, but it was ported to Python. So there's a link here for this, which I think is a nice visual way to do LDA in Python. So that's going to lead into a lot of visualization stuff next time. So yeah, I'm going to stop here.